Welcome to The Explainer. Have you ever been stuck on a problem where you need to find every single combination of items from a list, but you've got duplicates messing everything up? Well, today we're going to break down a classic coding problem that solves exactly that. And that question right there is at the very heart of a famous coding challenge called subset sum 2. It's a fantastic test of how you think recursively, and maybe more importantly, how you can do it efficiently. So, on the surface, the goal sounds simple enough. Take a list of numbers, find every possible subset. But here's the twist that makes it a real brain teaser. Your starting list can have duplicates, but your final answer can't. Let's make this real with a quick example. If you get an input like 1, 2, 2, we need to find all the unique combinations. Now notice how the subset 1, 2 only shows up once in the output. Even though you could technically make it with the first 2 or the second 2, we only count it once. That's the challenge we've got to solve. Okay, so let's put ourselves in the hot seat. You're in a coding interview, the pressure's on. How do you tackle this? Well, the most common starting point is just a good old brute force attack. It's a way to get an answer, even if it's not the best one. The brute force method is kind of like using a giant sieve. First, you just go wild and generate everything, all the possible subsets, duplicates, and all. It's a mess. Then, you dump that whole messy collection into a set, which is a data structure that, by its very nature, just throws out any identical copies. And finally, you just convert whatever's left back into a list. Simple, right? But messy. And look, it definitely works. It's a valid first shot. But any good interviewer is going to look at you and say, okay, now optimize it, because there is a pretty significant hidden cost to doing it this way. The problem is just all the wasted effort. For an input with n numbers, you end up generating an exponential number of subsets. We're talking 2 to the power of n. Imagine creating thousands, maybe millions, of duplicate lists, only to have some other process come in and clean up your mess. It's a huge drain on both your program's time and its memory. A much, much better solution is to be smarter right from the beginning. We want to design an algorithm that's clever enough to avoid creating these duplicate subsets altogether, building only the unique ones from the ground up. So, how do we build the answer intelligently? Let's dive into a smarter recursive approach. And you'll see, this is where one simple little trick completely changes the entire game. The absolute first step, the one thing that unlocks this whole optimized approach, is actually surprisingly simple. Before you do anything else, you have to sort the input array. Now, why is this so critical? Well, because sorting forces all the identical elements to group together. Once all the 2s are sitting right next to each other, our recursive function can easily see them and decide when to skip over them. This prevents us from building the same subset over and over. It's a tiny bit of work up front that makes the really hard part a whole lot easier. Now, with our numbers all sorted and neat, we get to the core logic. For each number we look at, we face a simple choice. Do we pick it to be in our current subset, or do we skip it? This decision, this fork in the road, is everything. Let's actually visualize this. Say we've already decided to pick the 1. Now, in the next step of our decision-making process, we see our 2 2s. We can absolutely pick the first 2, and that gives us the valid subset 1, 2. Awesome. But then, when we backtrack and consider picking the second 2 for that exact same spot, we have to skip it. And why? Because picking it would just give us 1, 2 all over again, the very duplicate we're trying to avoid. But here's the really clever distinction. We don't just ignore that second 2 forever. If we start a completely different branch of our search, say one that begins with the first 2 to create the subset 2, then when we move to the next element, we are allowed to pick the second 2. This gives us the subset 2, 2, which is brand new, totally unique, and perfectly valid. And all of this entire pick and skip dance, it all comes down to this one single elegant rule you see on the slide. This logic is the gatekeeper. It's what allows us to pick the second 2 when we're making 2, 2, but it slams the door shut when we try to make 1, 2 a second time. It only lets the unique combinations through. And that's really it. That one simple check, which only works because we sorted everything first, is the secret sauce. It's what turns this algorithm from a clumsy brute force machine into something truly elegant. Okay, so we've got our elegant solution. Now let's put it all together and see what this really means for performance and what the big takeaway truly is. Let's break down the cost. For time complexity,
Just think of it as how much longer the code runs when we add more numbers. Since for every number we have two choices, pick it or skip it, the number of possibilities grows exponentially. That's the 2 to the n part. The n times n is there because for every valid subset we find, we have to spend a little time copying its elements to our final answer list. For space, well, we have to store all those 2 to the n subsets, and that takes up a lot of memory. Finally, that auxiliary space, that's just the extra memory the computer needs for the recursion itself. And since our decision tree goes one level deeper for each number, that depth is simply n.
If there's one thing to walk away with from all this, it's how a simple, clever first step can completely unlock a beautiful solution to a really complex problem. Just by sorting the input, we turned a messy, brute force approach into something efficient and intelligent. It's a fantastic pattern to keep in your back pocket, which leaves us with a final question. What other tough problems out there are just one simple sorting step away from becoming easy?